So yes, Fredrik Mörk, that's me. I'm Mörk at Twitter. And as you may see, I'm wearing my shirt today. Exactly. So I'm 42 years old. First there was a time when I was not a developer. And then there has been some time when I have been a developer. And those two are approximately the same length today. I'm an occasional bird watcher. I am a newbie golfer, and I'm a not so newbie amateur photographer. I was born and raised here. I've been living some here, and I've been living some there. Right now, this is where I live. This is the client in Lund where I work right now. It's actually Click, where media also works. This is our office in Malmö, which is just around the corner here. And these are squares. I think that some of you has done this exercise before, about figuring out how many squares there are in this figure. I've tried this out at some people in my surroundings, and they come to some different numbers. Many reach around 25. Everybody sees that there are 16 squares, usually. Most people also notice that there is a big square. Most people notice that there are 4 squares in the corners. Then it starts to deviate a bit. Not everybody will find these 5, and also not everybody will find these 4. All in all, there are 30 squares to find in the figure. So what's the point with the squares? I have them here only to illustrate the fact that something as simple as a bunch of squares in a figure like this will give different interpretations of what you see. My background that we saw a glimpse of in the beginning here makes me perceive things in a certain way, and your background is different from mine, so you will see other things. This session is called API, the hidden user interface, but it could just as well be called the forgotten user interface, because I feel that often API design is something that happens by accident, or it's more of a side effect than the result of deliberate design work. When we talk about user interface in a traditional sense, usually we talk about things like buttons and text boxes and lists, things that a user can see on a screen and interact with. But users come in many different forms, and they interact with computers on many different levels. And different levels require different UI. If we talk about traditional UI and user interfaces, sometimes Google is pointed out as a good example. Maybe more so previously when they didn't have so many services. But it's easy to see why. It's a very clean design. There is essentially just one thing to do, and it's really hard to fail doing that. In the other end of the scale, you might find something like this. And if you put a bad tool in the hands of a user, their natural reaction, of course, would be to try not to use it, to try to do their job in some other way. An API is no different. If you put an API in the hands of a developer, they will try to not use it and solve their task in some other way. And if you force them to use it, they will be in a bad mood. They will go home in the evening and they will say that, well, today work sucked. And we don't want that. We want people that can be happy and go home and enjoy their beer or their bonsai tree or whatever floats their boat. So the question is, when we are working with something that will become an API, what can we do to avoid this and encourage this? Well, of course, to start with, there are some acronyms. There are always acronyms. Keep it simple, stupid. You ain't gonna need it. Solid. And solid, also a thing that I think that some are aware of already. It's a set of principles that were popularized about 10 years ago, a bit more, by Robert C. Martin and Martin Feathers. And it's a set of principles, and the idea is that if you follow these principles when creating software, you will create software that is easier to maintain and easier to extend. And these principles are about code, really. They are coding principles, but I think that they can be reused on many different levels. And they mean, from top down, that a type in a system should do only one thing. It should be open for extension but closed for modification. It should be able to be substituted for any subtype that you create from it. You should lean towards having a higher number of small specialized interfaces rather than a fewer number of more generic interfaces, and that you should lean on abstractions rather than concretions. I will look briefly into two of them, the single responsibility and the dependency inversion principles. So, single responsibility. What is a responsibility? If you take say an order system, it has the responsibility to manage orders. So is that a single responsibility? I would say that no, it's not. It's a rather large set of different responsibilities. So what is a responsibility really? This is one phrase that you usually see when you read text about the solid principle, that a well-defined type following the S has only one reason to change. I think that is about as clear. What is the reason to change? That can be anything. But as I see it, it's about behavior. And behavior is something that can be observed from the outside. So if I have a type that calculates a number, and I change the way it calculates that number so it becomes more efficient, I don't really change its behavior. Okay, it becomes faster, but the result is the same. So that is not a change in this context. And a type in an API should have only one such behavior that you can observe from the outside. A certain input gives a certain output. Given that, if we have an order manager, you hear almost from the name that no, it's not quite a well-designed type. It has many responsibilities. An order validator, on the other side, has a very clear responsibility. It validates an order. So what about dependency inversion? What is that about? The text that you often see is this one. High-level modules should not depend on low-level modules. And it always makes me think twice because I think it's wrong. Don't we always say that code on a higher level can depend on code on a lower level, but not the other way around? Well, that is true. But the choice of words matter here. High-level modules should not depend on low-level modules. It should depend on abstractions of lower-level functionality. Let's take the file system as an example. You have some code, you have some data, you need to store it in a file. So you open a file, put some bytes in there, and you save it on disk. Now you have a file on disk, but you also have code on a higher level module, your code, that depends directly on the lower level module, the file system. And what we want here is that we would want to depend on an abstraction of the file system rather than the file system itself. Leaning on such abstractions opens some interesting possibilities. For instance, it might be that when I store those bytes in the file, it might not be stored on disk, it might be stored in a database. It might be stored in the cloud. Perhaps it's not stored at all because we are running a test that doesn't really care about the file. It just needs to call that function as a part of the code being tested. The calling code doesn't need to bother really about the storage mechanism. It just wants an abstraction for storage. So we should think in modules. We should think in abstractions. And while talking about abstractions, we can touch the subject of abstraction levels. Let's stay in the file system. How do we describe a file? What kind of concept do we have for a file? Let's say that we have a write stuff method. It takes a stream to write something to, and it takes a string with the content to store. Then if we have a read stuff method, it should take a stream to read from and return the data as a string. The concept file is represented by a stream, and the content is represented by a string. And when deciding on abstraction levels, how do I describe a file? What kind of type do I have to describe a file? We sometimes move along something that I call the sophisticated primitive scale, where primitive is something that is very close to the actual representation, the file on disk, while sophisticated is something that is pretty far from the real thing. For instance, a data stream is pretty close to what we are talking about actually, a file on disk, while a file name is a concept that is quite far away from the actual file on disk. And this choice is not unimportant. More primitive building blocks can be more, let's say, combinable. If you take a pirate ship in Lego, it works excellent as a pirate ship. But if you take those pieces and try to build something else, that is pretty hard. If you use more primitive pieces, you can build pretty much anything. You can build a wide variety of things, given that you have enough of them. So it's better to expose the most primitive, simplest type that gets the job done. If you take this method here, we have a do stuff method. I will be diving into some code, not a lot. There are this and a couple of more code examples, but I hope you can bear with me if you're not developers. So we have this method, do stuff. It takes a list of items that it will do stuff with. In this C# code, we use the concrete type list of t. So the first thing we should do is to instead use the abstract type, the interface iList of t. Now suddenly we don't need to agree to use exactly list of t, but I can pass in any class that happens to implement this interface. We don't need to agree on the implementation anymore. Even better, perhaps, I could pass in IEnumerable of t, which in the .NET world is supported by essentially any data type that represented a data sequence, any array, anything that is a list. Also, this is not only a technical choice about what we can do, it's also about communication. Because iList is a mutable type. You can add and remove things from it. It has add and remove methods. IEnumerable is a read-only interface. So by declaring my method like this, I clearly communicate that I will read through this list. I will read the items, but I will not change the content of the list. I will not add anything. I will not remove anything. I might modify the items themselves, though. So that was some technical background, we can say. Now I want to move into some software aspects. If we design an end-user interface, the user will have some sort of starting point. There will be a button saying, start here, very clear. How do we do that in an API? It's not so obvious because the API is sort of hidden in its nature. Well, the best thing is if we design the API in a way so they don't need to search for stuff but just happen to find functionality where they expect it. There is a guy called Jacob Nielsen running a site called useit.com for many, many, many years. He at least used to specialize on web user experience. And he coined something called the Jacob's law of the web user experience. And it goes like this. Users spend most of their time on other websites. The idea is that if you would design a website, a user comes here, and their expectation of how this thing works will be entirely based on their previous experience from other websites. Users spend most of the time in other APIs. It's just as true. A few years ago, I had an assignment with a client. They had a software for running automated tests, essentially. This software had a scripting environment with some sort of VB dialect in it. And I had a task one day to write a script that, based on a test case, navigated up the hierarchy of test cases and found some folder and did something there. So I sat down to write this script, and I figured, okay, I have this test case, .parent, and parent didn't exist. There were no such property. So I had to search the internet, read documentation, and I found that there was such a property, but it was called father instead of parent. So I sort of reacted the same way, giggled a bit, and I got the job done. But it slowed me down. And not only the first time when I had to search for it, but every time where I was to use this property, I started just as a reflex to type .father. So every time I had to sort of take a step back and find the right way. So it slowed me down every time. This is another more recent example that I have come across. This is from a REST-based API, a JSON object that I get back, some entity that has a timestamp when it was created. This was what I had expected to find. This date and time value here is essentially an ISO format date. You can toss that string into virtually any coding library on the planet, and it will be able to parse that and convert it into some date-time object. This is what I got. And I thought, what? I mean, this time zone offset in the middle of the expression. Okay, it's closer to the time, I can give them that, but then what is the time doing in the middle of the date? And also, this thing here I find especially interesting. What other weekdays could September 11th, 2013 have been? This can only cause problems. I'm not going to give away the name of the company, but it's a huge player, so I was quite surprised to find it, I can say. Users spend most of the time in other APIs. So other APIs will form the expectations of what is expected from your API. And we should try to use that power of habit instead of fighting it. And naming is one of the first things that meets the eye. It's what the API is about, essentially. And it's really hard, but it's important to get it right. And we should really spend time on that. I mean, traditionally, if you look at user interfaces that developers do, they look pretty much like this awful screen before here. And I think that we sort of stay inside the surface, underneath the surface, and we don't really think about polishing the outside of it as much as user interface design does. And when it comes to naming, the first rule of naming is don't be creative. It's a bit boring, but it's effective. Father versus parent in the example before is a brilliant example of that. So you should study conventions and patterns in the environment where this API is to be used. Watch the base class libraries if there are any, read guidelines, and look at certain words that can be interesting to follow. For instance, get, fetch, and find. What are the semantics around those words? Should it be save or store, for instance? Remove or delete? Remove delete is especially interesting because many environments have IntelliSense, and R and D are quite far away from each other, so they will not show up where the user expects if you pick the wrong one. So we should follow these patterns because the users will recognize them, and recognizing stuff is so much easier than learning stuff. And naming is hard, but very important to get right. But the details inside also matter. Let's say that we walk into a restaurant and we want to eat there, but first I need to go to the bathroom, and I go in there and it's really filthy. What does that tell me about the restaurant kitchen? Well, nothing essentially, because I haven't seen it. But I tend to seek patterns. I imagine that if it's really filthy here, it's probably really filthy there as well. And we want, if I use an API and see the surface, I will want to know that the stuff underneath is that you pay attention to details in there that is done. We, for instance, expect that the developers have paid attention to, for instance, how they use shared resources in an asynchronous environment, for instance. We want to make sure that they release resources once they are used and don't need them anymore. We want them to pay attention to strings that come in that will be parsed into SQL statements, so we don't open up for SQL injection attacks and stuff like that. But we won't know anything about these details because they are inside the API, and we only see the surface. So if the surface is not good, that can actually become a credibility issue. If they didn't mind that detail, did they mind that detail? Also, if you're not building a REST API but rather a class library, the compiler is a really good friend to have. It's really efficient because it tells me what's wrong. You cannot do that, it says very clearly. And then I can go back and correct it, and I compile my code, and the compiler is silent, and everything is fine. Or could be, at least, because syntactically correct code and correct code are not the same thing. Let's say that we have this code here. I have this type here. I create an instance of it, and I call a method, and the compiler goes in there and checks, yeah, it exists, and this method exists, and everything's fine. Code compiles, and then I run it, and bang, it turns out that, yeah, you need to call this first. There's no chance for the compiler to detect that. And also, if you don't have tests that detect it, it can easily slide into production and manifest itself as a bug that can be really hard to find. And there are, of course, many ways to fix this. Make sure to just pull in whatever you need in the constructor, hide the constructor and make a factory, whatever. Just make sure that when the user gets an instance of this type, it's ready to be used. And these kinds of temporal dependencies that you need to call things in a certain order, I think is something that should be avoided at all cost. Also, assumptions are something to pay attention to. I had a Swedish teacher when I went to school that loved the idea of essay writing. We did that all the time. And she had this mantra that she always came back with, and that was to never assume or always assume that the reader doesn't know anything about the stuff that you're writing about. And that was a quite good thing to keep in the back of the head when I was writing things, because it reminded me to include things that were obvious to me but might not be obvious for somebody else. Much in the same way, when building a class library or some sort of API, it's a good idea to don't make any assumptions about the calling client, for instance. Because if you don't do that, the chances are that you will support a wider variety of clients because you don't lock into one certain type. Also, it's a good idea not to assume anything about the knowledge of the developer writing the code to call into your API. That they don't know anything about the technology that you encapsulate, for instance. Because if you put those goggles on, you will probably find simpler names for things and simpler ways to do things with your API to actually succeed. Also, this is important to remember, that graphical user interface can change. APIs can't so easily. Let's say that we release a piece of software, people start to use it, and we realize that we get many support calls about they don't find this one feature. So we go back, fix that UI, make that feature stand out a bit more clearly, and we ship a new version, and people are intelligent, so they will see, wow, this changed a bit. And they will find this button, and they will use it, and they will hopefully become more efficient. If we do that with an API, stuff breaks, essentially. Things will stop working. Compiled code isn't smart. That means, slightly bluntly put, that we have exactly one chance to get it right. And I would even push it so far as to saying that once you publish an API, that API is not yours anymore. It belongs to the users of it, and it's not yours to break. You can fix things under the surface, but the API is not yours. So think about versioning from the start. So let's say that we have this API we have done, a class library or something, and it's great and people use it and they're happy with it. How do we keep it great? How do we keep it from growing into some bloat that is essentially unusable? Because there will at some point be somebody coming saying that, hi, I use your API, this class library, and it would be really great if it had this feature. And the default answer is no. Also a bit boring, like don't be creative, but very efficient. Because the user, when they come with this feature, they come with a problem maybe. They don't really come with problems. They come with solutions to their problems, to their specific problems, which might not be shared by other users. I saw a video a few years ago, which was a sort of talk/interview with Anders Hejlsberg from Microsoft, who created the C# language, and the team who was then building the C# compiler. And one of the things they talked about was the thought process around bringing in new features to the C# programming language. And this was a very important figure in that process. When somebody came with a feature request, this is the value assigned to it, minus 1,000. It has negative value to start with. During discussions with whoever brought the feature in, they need to show that it holds so much value that it comes up above 0. And then we could think maybe pulling it into the language. Of course, it was not a checklist. Does it do this? Okay, that's 5 points. Does it do that? Okay, it's 10 points. But more a thought pattern. But it's very important to remember that a new feature doesn't have value by itself. Exactly. Because it should also be kept in mind that the new feature should be valuable not only to the person or the customer coming with a feature request, but for a wider variety of users. And I would say that good features, good design in general, is things that benefit many rather than fewer, even if the few are big and loud. Also, important to remember is that the API that I'm building is a tool. It's not the means, or it's the means, not the goal. If I'm doing construction work, I will use stuff like this. I will use like hammers and saws and drilling machines and things like this. But my goal is not to use a drilling machine or a saw. My goal is to shorten this piece of wood so it fits where it should be. And if I need to spend time to figure out how to hold the saw or how to hold the hammer or how I get the drilling machine started, something is wrong. I don't want to spend time with that. It should just work as I expect it to work. And our APIs, the things we build, they are tools for others to use. They are not in the business of like copying files or serving HTTP requests. They are in the business of maybe making a system that will book customer appointments or update a calendar or serve a shopping site. They want to make money. And then they want to go home and have that beer and work on their bonsai tree, or maybe write that game. So important to remember is that the API is a user interface. In fact, it's nothing else than a user interface. Often, I think that the API is what happens to be on top of the stack when the functionality is done. But that is not an API, that is functionality on the top of the stack when the functionality is done. If we look into end user interfaces, there are many design patterns that we use to disconnect the user interface from the functionality, like model view controller and all sorts of things that we do to not have tight coupling there. APIs could probably like the same kind of love. Also, make sure that anything underneath the API is modular and combinable. Design it as building blocks that you can combine into many different things. Don't make too much assumptions of what the users should be able or not be able to build from it. Remember to be very deliberate in any decision in the API. Why are things called? Why is this method called what it's called? Why do I use this type to represent a file? Why do I name this parameter this way? Why is this function in that type? And so on. All these decisions should be very deliberate. The API is a user interface. So next time you're building something that becomes an API, don't force your users to think about where and how, but let them focus on what. Thank you.